Well, hello, welcome everyone. So today the video is on angular momentum and angular impulse question, but this is only for the students who are doing AQA engineering options. So let's just get started. All right, so question number 1, you have a gymnast that dismounts from an exercise in which he swings on a high bar. The gymnast rotates in air before landing. So, okay, in position 1, the gymnast has to let go of the bar. His body is fully extended. Position 2 shows the rotating gymnast let go of the bar. Fine. His knees have been brought closer to his chest into a tuck. So this is my hint here. He's telling that the knees have been brought closer. That means the mass has been brought closer to the axis of rotation. So I has decreased. So what has happened to omega is it increases. All right, let's go to position 3. His body is once again fully extended. So I has increased, omega decreases. All right, let's just see. Explain why the moment of inertia about the axis of rotation decreases when his knees are moved towards the chest. Why I decreases? Okay, so let's just see how many marks. 3 marks. So first, as the mass is brought closer to the axis of rotation, your mass is being brought closer to the axis of rotation, so I decreases and omega increases. Okay, so first, mass is now closer to the axis of rotation. Okay, axis of rotation, so we got it. So this, so mass, because mass is now closer to the axis of rotation, so I decreases, and because there is no external torque, okay, as torque is 0, you write in full words, as torque is 0, L angular momentum remains constant. You write in full words, angular momentum is constant, therefore omega increases. Okay, so moment of inertia decreases because mass is brought closer, so we have answered this one. Okay, because mass is brought closer to the axis of rotation, and then we have explained the effect this has on angular speed. If you write just omega increases, you have not explained why it has increased. It has increased because I has decreased, torque is 0, L should remain constant. Then you have explained it. Otherwise, you've not explained, you've just stated omega increases. Let's do the next one. Calculate the angular speed. So what's happening? I is 13.1, omega we don't know. In position 2, I is reduced, so omega increases. What's the angular speed? So the product should remain constant because angular momentum is not changing. I omega should remain same. So just using your calculator then, I have, okay, so I have 4.1 times 14.2 divided by 13.5, that is 4.312, and then writing in up to 1 decimal point is 4.3, so 1 decimal point, 1 decimal point, 1 decimal point, 4.3 radians per second. The gymnast stays in the tuck for 1.2 seconds, fine, so I have the time, and because he's not changing I in the tuck, omega fairly remains constant. In the tuck is 14.2, so my omega is 14.2. Number of rotations, so 14.2 radians per second. So in 1.2, what will be the angle it will rotate? It is 14.2 times 1.2, just doing that, 14.2 times 1.2 is 17.04, and then what you do is you need to get rid of the radians by dividing it by 2 pi. So just doing that, okay, so it is 2.71, so I'm writing 2.7 because all my numbers in the question are up to 1 decimal point, so same here, but that's not the complete answer. It's just asking me rotations, right? So just 2.7 rotations. Okay, now the gymnast repeats the exercise. The height of the bar remains unchanged. State and explain 2 actions the gymnast can take to complete more rotations during the dismount. Say if he wants to make more rotations, that means it should have greater starting angular speed. So if he has a greater starting angular speed around the bar, because when he started he was rotating himself around the bar, so if he rotates, build up a greater starting angular velocity, it would end up reaching to a final higher angular velocity and hence more number of rotations. Okay, during the dismount, so first it could just say start with build up larger angular velocity. So you're building up larger angular velocity around the bar to reach a greater height. Okay, so when you have reached a greater height, and then when you reach to a greater height, and then you will end up rotating faster in the tuck to rotate faster in the tuck. Okay, so this could be one option. What could be the other option? He can get it can be in the tuck position for longer. If he's in the tuck position for longer, then also it'll end up moving for longer than 1.2 seconds, because if it is let's say 1.5 seconds or 1.8 seconds, larger time means it'll end up making more angles or more rotations. Okay, let's just do the next one. On a still day, a gust of wind from a passing vehicle imparts an angular impulse. So I have an angular impulse of this much to the sign, which accelerates from rest during a time of 2.8. So I have an impulse which is 1.2. Acceleration starting angular velocity is 0. Okay, I'm not going to write this. I'm going to write impulse. Starting angular velocity is 0. Time taken is 2.8 seconds. Moment of inertia. See, I write impulse because I is for moment of inertia, which is 4.8. Assuming that the frictional couple acting on the sign is negligible, calculate the angular momentum acquired as a result of angular impulse. Okay, so what is impulse? Angular impulse is, impulse is change of angular momentum. Again, final minus initial. Initial is 0 because it's starting with a 0. And the final angular momentum, this is what you have to find. And this is nothing but the impulse. And impulse is 1.2. That's it. So my angular impulse is 1.2 kg meter square radians per second. So that's my final angular momentum as a result of the impulse. The angular speed of the sign immediately after the impulse has been imparted. So now it's asking omega. You got the L, just divide L by I. 1.2 divided by 4.8 times 10 to the power minus 2, which is 1.2 divided by 4.8 times 10 expo minus 2, equal, I have the answer as 2.5 times 10 to the power of, so I have 25 radians per second. 25 radians per second. So that's my omega. Yeah. The average torque. So now this is asking average torque. Okay. So now torque is not torque times time is impulse. I have impulse which is 1.2, and this torque acted for 2.8 seconds because it was accelerating for 2.8 seconds. So then dividing 1.2 divided by 2.8 is 0.43 Newton meters. Okay, yeah. A second sine of the same type. Okay, so sine is of same type, same moment of inertia, continue to rotate for 14 seconds after an impulse has been imparted. Okay, so it continued rotating for this much. Now the friction brings it to rest. So that means my final angular momentum is 0 because the friction is bringing it to rest. Initial angular momentum would be I omega. I is same as the previous one, so which was 4.8 times 10 to the power minus 2, and omega is 30. Now calculate the number of turns made by the sine during this time. Say we don't need angular momentum, we just need angle, which is so what we do is we use this formula. Remember, S was average velocity times time. So you can use the same. Final plus initial divided by 2 times t. Final is 0. Initial is 30. Time is 14 seconds, which is 15 times 14, which is 150 plus 60, that is 210. Now this 210 is in radians. Now it's asking you number of complete turns. That means you need to convert this into revolutions by dividing it by 2 pi radians. Now, okay, I'm not that good. I need to use calculator to get 210 divided by 2 pi is around, I have 33.4222. So I'm going to take it as 33 rotations because all of my question digits had 2 significant digits, 14, 30, hence 2, 33 rotations. So the questions are generally not that difficult. Only thing is because they have too many formulas, too many concepts, if you do not practice, it becomes a little tough. But if you have practiced enough, this is the easiest bit. It is, as you know, physics is very easy if the concept is just clear. Okay, so I have next video I'll be doing some questions on conservation of angular momentum, more questions on angular momentum. See you then. Thank you for watching. Bye bye.